Very quick word now about quantities and units. So quantities like mass, length, time, they all have to be in the standard international units. So kilograms for mass, meters for length, and seconds for time. And you need to be able to convert from, for example, grams to kilograms and kilometers to meters and so on. And also the derived units, so things like speed or velocity, which is in meters per second. If you were given a speed in kilometers per hour, you'd need to be able to convert that into meters per second. All the things that you work out in this year have to be in these standard international units. So let's do a little bit of practice and let's see how you get on with that. Okay, so here's a little bit of practice for you. Write the following quantities in SI units. So I'll give you a moment to just have a go at these and see if you can convert them into meters, meters per second, and so on. And they're going to go through it in a moment. So pause the video, have a go, and I'm going to go through it soon. Okay, pretty straightforward, the first three, I think. So working out 5.4 kilometers in meters, well, there's 1,000 meters in a kilometer, so that's going to be 5,400 meters. For question 2, we've got a mass in grams. We need to divide by 1,000 to get that in kilograms. 1,000 grams in a kilogram. Question 3, this is a measure of speed or velocity, so kilometers per hour. So we need to work that out in meters per second. So to go from 40 kilometers to 40 meters, we'd have to multiply by 1,000. And then to convert from per hour into per second, we're going to divide by 3,600 because there's 3,600 seconds in an hour. And if you work that out on your calculator, you get 11.1 recurring meters per second. Okay. 50 grams per centimeter squared. This one's a bit of a tough one, really. It's a measure of density, but we need to first of all change it into kilograms, and then we're going to think about how we can go from per centimeter squared to per meter squared. Okay, a little bit tricky there. The first thing we need to do is to go from grams to kilograms. So 50, to convert that into kilograms, we would divide by 1,000. Okay. Now, if the area is centimeters squared, but we're dividing by centimeters squared, to convert that into per meter squared, we're actually going to have to multiply by 10,000 because it's 100 centimeters in a meter, but we're squaring that. So multiply that by 10,000. And that leads to 500 kilograms per meter squared. Okay, I wonder how many of you got that one right. Okay, we're going to talk a little bit about forces now. And the main forces that you'll be dealing with are things like weight, normal reaction force, tensions in strings, and if you have something that's pushing an object, maybe there's a thrust involved. So we're just going to go over this terminology and what it actually means in practice. So we have a situation here where we've got a book that's at rest on a bench, okay, or a table, and we know that if the table wasn't there, that book would just fall down to the ground. You know, it's like dropping an apple. We know it's going to fall down and hit the ground. So the table is actually preventing that book from falling down, which means that there's got to be some force acting on the book by the table. And that's what we call the normal reaction force, and we've labelled it R here. So we've got the weight, which is acting vertically downwards. The normal reaction force actually acts at 90 degrees to the surface it's on. So let's say we had a different situation. Let's say we had maybe a cylinder, and we had a bench or a wooden beam or something that's at rest on that cylinder, there's going to be a normal reaction force here, but that's going to be acting at 90 degrees to the actual bench. Okay, so where the bench and the cylinder interact, there's going to be a 90-degree normal reaction force acting there. And the weight of the bench would be acting vertically downwards. Okay, so normal reaction force and weight. Friction always acts in the opposite direction to the way an object is moving. So if we're pulling or pushing a book along the table, then the frictional force is going to act in the opposite direction. Here we have the blue arrow showing the direction of motion, and the friction acts in the opposite direction. Now, something that might be a little bit confusing to some students, these forces are exactly the same. So this, if we have an object that's moving to the right, we could represent the friction as an arrow pointing into the object from the right hand side, or we could model it as an arrow coming out of the object, so on the left hand side. So it's just the direction that's really important here. If we have a string that's pulling a book along, then the tension is the force that's acting on that book, okay, and it's the tension in the string. So think about the direction the book's moving, and the tension is pulling that book along. Another way of moving the book to the right is by pushing it, and imagine that we had a rod or even a spring, and we push the spring into the book, and we know that spring is going to compress, it's going to get shorter, and it's going to push the book along. So we call that thrust or compression. So those two words are meaning the same thing, kind of like a pushing force. And we tend to use these when we're looking at tow bars, so like a car pulling a trailer along. If the car's accelerating, then you're going to have a tension that's kind of like trying to stretch the tow bar. But let's say, for example, that the car was to brake, then that trailer is going to tend to try and push the car along because it's got momentum, and then you'd end up with a compression in the tow bar. The trailer would try to squeeze the tow bar, if you like, or compress it. So we tend to use this when we're looking at connected particles, thrust and compression. Tension we're going to deal with quite a bit in problems in mechanics. And friction, the first part of mechanics will just deal with a constant friction, so that if there is any friction involved, you'll just be given a value that's constant. But next year, when we look at friction, you'll actually get to work out what the value of the friction is. And it's a factor that's related to the normal reaction force. Okay, but we'll deal with that next year. Okay, so have a little think about this book that's actually on an inclined table. And what are the forces acting on this book here? Well, let's imagine that it's being pushed up. Okay, we've got the red arrow that's pushing it up. What would we call this blue arrow? What would that be? Well, that would be, if it's a rough surface, then that would be the friction. And this purple arrow acting downwards, that's going to be the weight. To clarify that, if you have a mass of, for example, 1 kilo of a book, then the weight is the mass times 9.8. So it would be 9.8, and that's measured in newtons. So just to mention that for you. And then again, the normal reaction force is acting perpendicular to the surface that the object is at rest on, or is it moving on. Okay, we just mentioning these really, we don't tend to do much with buoyancy, but buoyancy is just a kind of upwards force. You have the weight of a boat on a river or stream or something, and the weight's acting downwards. So it's the buoyancy that keeps that, there's the force that's acting on the boat that's keeping it stable in a vertical direction at least. Air resistance, again, that's acting in the opposite direction an object's moving. So in this situation, we've got a parachutist that's dropping vertically downwards, so his weight's pulling him down, and the air resistance is acting upwards. But it could be that he's travelling to the left as well, in which case the air resistance would be acting in the opposite direction that he moves. Okay, a little bit of practice for you. Just see if you can label these four forces. Okay, think about an aeroplane. Okay, think about some words that we might not have used already, and see if you can label these four forces. I think you should be able to get two of them, but you might not get all of them. So just pause the video, have a go, and I'll let you know what they are in a moment. Okay, well, and we have certainly the weight of the aircraft, which is acting downwards. So what would be this force acting upwards? It's not going to be a normal reaction force because this aeroplane isn't at rest on anything. Okay, you only get a normal reaction force when you have an object that's at rest on another object or is moving across the surface of another object. But this one is just in the air. This airplane's in the air, so A we're going to call lift. Okay, not normal reaction force. D might have given this one away a little bit. It could be drag or resistance, air resistance. And for B, well, this is going to be the thrust produced by the engine. Okay, or the pulling force there. Right, a little bit of practice for homework, guys. Again, have a go at this as exercise, and any problems we can discuss in class. In this section, we're talking about the difference between vector quantities and scalar quantities. Now, a vector quantity has got both magnitude and direction, whereas a scalar quantity has only magnitude. Here you have some examples of vector quantities, so displacement, velocity, acceleration, and weight. They all have magnitude and direction. A person's weight, for example, has the direction vertically downwards because that's the way it is accelerated due to gravity. Scalar quantities, on the other hand, have just a size. Now, a common problem for students is the difference between displacement and distance, and we'll be going through some examples in a minute to show the difference between those two. Essentially, displacement can be positive or negative, but distance is only positive. Same thing with velocity. Velocity can be positive or negative, and speed is just the magnitude part of the velocity, so we ignore the sign. Time and mass are just positive values. Okay, and like I said, we tend to be working in just one dimension. Imagine a person standing on the edge of a cliff and they throw a ball up. As the ball is above the person's head, if we've chosen upwards as positive, it will have a positive displacement. If the ball then travels over the edge of the cliff and goes down and hits maybe the beach or the sea, and we've chosen upwards as positive. So I'm going to go over a few examples of that type of thing in a moment. Here we have a person wants to travel to a baker's, and we have 4 different journeys that this person takes. The baker's is 100 meters away from the person, so we have the person at position A and the baker's at position B. Now, if the person travels from A to B, they've actually travelled a distance of 100 meters, and the displacement is 100 meters as well. We've chosen to the right as positive, so it's a positive displacement. If the person travels from A to B and then comes back towards A by 50 meters, then the total distance they've travelled is 150, but the displacement is plus 50 because it's 50 meters away from the starting point. and it's to the right, which is positive, so it's a positive 50. In this third scenario, the person travels from A to B and then back to A again, so they have travelled a total of 200 meters, but their displacement is 0 because they've ended up where they started. The force situation, force journey, the person just travels to C, which is 30 meters away, but it's a negative 30 displacement because it's in the opposite direction to the way that we've chosen as positive. We've chosen to the right as positive, so the displacement is minus 30. Here we have 4 different objects, and we want to describe the motion of each of these objects A, B, C and D. Now again, we've chosen to the right as positive. That's entirely up to you, whichever way you want to choose. But here we've chosen to the right. And for object A, we have a positive velocity and a positive acceleration. So it's traveling, the particle or object is traveling to the right and it's accelerating, so it's going to get faster and faster to the right. Particle B has got a positive velocity but a negative acceleration. So even though it is traveling to the right, it is slowing down. And at some point, it will slow down so much it comes to a full stop. And then, because the acceleration is negative, it will start to travel backwards. Particle C has got both a negative velocity and a negative acceleration. So particle C is traveling to the left. Okay, so in the opposite direction to the way we've chosen is positive. Its velocity is negative, so it is traveling to the left, but it's speeding up because it has a negative acceleration. It's getting faster and faster to the left. Particle D is traveling to the left, but the acceleration is positive. So even though it starts off traveling to the left, it's going to slow down until it gets to a full stop. And then because the acceleration is positive, it's going to move it to the right. So initially it's traveling to the left, but slowing down, and then it will start to speed off to the right. So at that point, when it changes direction, the velocity will change from negative to positive. Here we're going to talk about how we can describe a vector in terms of the sum of scalar multiples of the unit vectors I and j. So here we have the unit vector I, which is a vector of size 1 pointing horizontally to the right, and the unit vector j, which again is a vector of size 1 that points vertically upwards. Now by multiplying each of these two vectors by scalar multiples and combining them, we can get any vector. Here's an example. Let's say we have the vector A, which is 3i plus 3j. So it's 3 is the scalar multiple of the unit vector I, so 3 lots of I plus a scalar multiple of 3 times the unit vector j. We're adding them together. How would we draw that? Well, we need a starting point, so let's say there's a starting point there. So we'd go across by 3. Okay, so we're going 3 lots of the unit vector I, so across by 3, and then we're going to go up by 3, so 3 lots of the unit vector j, and our vector would be like that. So again, across and up. We're going to start our vector there and finish it at the end point, and put an arrow on to show the direction. So there's 3 and there's 3 there. Let's try another one. Let's say we have the vector B. Incidentally, I'm underlining these letters, folks, to show that they are vector quantities and not scalar quantities, or variables like x and y. So if you see something underlined, it means it's a vector. In textbooks, they tend to use bold text to show vectors. So if you see something in the kind of bold font, then it could be a vector as well. Okay, so vector B is minus 4i plus j. So let's sketch it again. You will need to be able to sketch vectors like this because it will help you understand the problem. So minus 4i, this time we're going to go to the left by 4 because it's a negative 4i, and then plus 1. So that's minus 4 and that's plus 1, and our vector would look something like this. Okay, so there's two examples of vectors in terms of I and j notation. You might be more familiar with seeing them in terms of column notation, so 3, 3, or for B we've got minus 4, 1. Personally, I prefer column notation. It makes it very simple when you're adding vectors together. So we'll do some examples of that in a moment. Going back to the point of this section is how do we use Pythagoras and trigonometry to work out the magnitude and direction of a vector? Well, these are all right angle triangles, and that's because I and j are both orthogonal or 90 degrees to one another. So in order to work out the magnitude of a particular vector, the length of the vector, we're just looking at the length of that hypotenuse in this right angle triangle. So for A, if we wanted to work out the length of A, let's denote it like this. This means magnitude of the vector A. The two horizontal lines either side mean magnitude, and we're just going to use Pythagoras. So it's going to be the square root of 3 squared plus 3 squared, which is the square root of 18. Okay, or if you want, you can write it as 3 root 2. Same thing for B. Let's work out the magnitude of B. So again, the square root of, we can ignore the sign here because minus 4 squared is going to be 4 squared. It's going to be the same thing. You're going to get 16 there. So I'm just going to ignore the sign. 4 squared plus 1 squared, which equals the root of 17. Okay. So that's how we work out the length of the vector, or the magnitude. How do we work out the angle, or the direction of the vector? Well, that's just using a little bit of trigonometry. Let's do this one in red. Let's say we want this angle here. Okay, the angle alpha, well, we can use trigonometry because we have a right angle triangle. So tan of that alpha angle would be the opposite over the adjacent. And in this case you would get, if you did the inverse tan of 1, you'd get 45 degrees. Okay, and for the next one, let's say we want this angle here. Tan of alpha would be 1 over 4. Okay, so if you wanted to work that out, just do the inverse tan of 1 over 4, and you get 14 degrees. Now, you may be asked for the bearing of these vectors, in which case you'd have to work out, in the case of A, you'd have to do 90 minus alpha to get the bearing, or in this case, remember bearing is from north and it's clockwise, you'd want the whole of this angle here, which would be 270 degrees to get to this horizontal line, plus another 14, which is alpha. So that would be 284 degrees. This one you just take alpha away from 90, so that would still be 45 degrees as a bearing. Okay. Here we have an example where we're given the velocity of a particle as a vector, and we want to work out the speed and the angle the direction of motion of the particle makes with the unit vector I. So what's the angle that the vector makes with the horizontal? Right, let's start off with part A. So we need to work out the speed of the particle. The speed is actually the magnitude of the velocity. So let's just write that down. So we're just going to do the square roots of, in this case, 3 squared plus 5 squared, which is the square. You're asked to give your answers not exactly as surds, because mechanics isn't, we don't always want the exact answer, because we might have done some rounding. For example, using gravity, we round to 2 significant figures and use 9.8. So exact answers aren't always appropriate. So instead of the square root of 34, we might want to write down the actual decimal value, which is 5.83. Okay, so speed is in meters per second. So that was part A. Part B, the angle, the direction of motion of the particle makes with the unit vector I. So if we sketch this vector, we're going to start here, we're going to go across by 3, we're going to go up by 5. So there's the actual vector. So the particle is travelling in the direction of its velocity, and we want the angle that that makes with the unit vector I. Well, remember the unit vector I is horizontally to the right, so we want to know what this angle is here. Okay, let's just put that in, 5 and 3. So tan of the angle is equal to opposite over adjacent. So we get the inverse tan of 5 over 3, which is 59 degrees. Okay. So just make sure you get the numbers in the right place, the scalar multiples on the right sides of your triangle. Do sketch your vectors so you can see exactly what's happening. And there we go. That's how you work out the speed and the angle of the vector. Let's try another one. Here we have a man that's walking from A to B and then from B to C, and we're given his displacement vectors from A to B and from B to C. We want to work out the magnitude of the displacement from A to C. So if he wanted to travel from A to C, how would he have to do that? Well, let's just write this down as in terms of vector notation. So the magnitude of the displacement from A to C is basically the sum of the two displacements. We need to work out the displacement vector first, which is the sum of the two displacement vectors, AB and BC, and then we're going to work out the magnitude of that. So let's write down AC. I'm using this notation because it's a little bit easier when you have points on a drawing to write it like that. So the vector AC is the sum of the vectors AB and BC. And I'm going to use column notation because it's quite easy. I don't have to keep writing I's and J's out all the time. And BC is 5 minus 12. And of course, when you're adding two vectors given in terms of column notation together, then you're just going to add the rows together. So 6 plus 5 is 11. 4 plus minus 12 is minus 8. So that's the displacement vector. We want to know the magnitude of that. So I'm going to use those two bars again. So that means the magnitude of vector AB. And that's just going to be the square root of 11 squared plus 8 squared. Okay. And work out what the decimal equivalent is for that. We get 13.6. Okay. Now displacement is in meters, so the magnitude would also be in meters. We want to know the total distance the man has walked. Now, in order to work that out, we need to work out the distance he walks from A to B, and then the distance he walks from B to C, and add them together. So we need the magnitudes of the vectors AB and BC. Okay, so the magnitude, sorry, that was AC there. The magnitude of AB is equal to square root of 6 squared plus 4 squared. And if you just pop that in your calculator and work out what that is as a decimal, we get the value 7.21. Okay, same thing for BC. How far is it from B to C? So we're going to pop in 5 and 12, which is the square root of 169, which is exactly 13. And then the total distance from A to C is just the sum of those two values. So we're going to get 20.2. We just round it to 3 significant figures. Okay, and there you have it. So the total distance the man has walked from A to C. Okay, a little bit of practice for you. Exercise 8D and the mixed exercise as well. Very good practice for you folks. There's going to be some quite tricky questions in there. So any problems, bring them along to class and we'll go through them. Okay, just to summarise what we've done in this chapter, we've looked at mathematical models and how to construct a mathematical model to simulate a real-life problem, and modelling assumptions, how they can simplify our calculations by taking assumptions like no air resistance. Okay, we've looked at the SI units, those common ones used being mass, length and time, and what is a vector? Okay, how can we describe a vector in terms of the unit vectors I and j? How do we work out the magnitude and direction of that vector? Also looked at the fact that distance is the magnitude of the displacement vector and that speed is the magnitude of the velocity vector. And given the constant acceleration, that particles travel in the direction of their velocity. Okay, so there's just a summary of the key points of this chapter.